Okay, today we're going to calculate the reaction quotient Q and compare it to the value of Kc or Kp in order to determine whether or not a reaction is at equilibrium. We're going to do that with 80% accuracy by completing our quest on general and gas phase equilibrium. Number 2. We're also going to predict the direction a reaction will shift to reach equilibrium, also with 80% accuracy. Okay, so a large part of what we're doing for these first couple of videos is all review, because we've been looking at these things in the context of both the stoichiometry, electrochem, thermodynamics, and kinetics units. So all the stuff we've been doing so far to this point in the year has led to this or had some connection to this. So if we're looking at the value of K, we know it's the ratio of products compared to the reactants at equilibrium. So we can use this value to predict the direction of the reaction and which way the reaction will shift. So when K is large, large meaning greater than 1, that means that the products are favored. If we think about that in terms of our fraction, right? If we have larger products on the top and smaller reactants, that means we've got a large numerator divided by a small denominator, which means we will end up being greater than 1. Right? If you divide, say, 1 by 0.1, you're going to get a number larger than 1. If we're looking at the reverse direction, if reactants are greater than products, then you could have a small numerator and a large denominator, which gives you a decimal or a tiny fraction, which means our K value is going to be less than 1. So what that means is that when our K is greater than 1 and large, we are shifting to the right. We are favoring the forward process. When K is less than 1, we are favoring the reverse process. Okay, so we can also manipulate equilibrium constants much like we would in thermodynamics with delta H or in electrochemistry with our E naught. With equilibrium constants, there are a couple of special rules. So we know that in the forward direction we have products over reactants. If we go in the reverse direction, so I'm going to make a note here that this is showing the reverse. If we're going in the reverse direction, our equilibrium constant in the reverse direction will be 1 over K. So it's the reciprocal. Nice thing is it's easy to remember, reverse and reciprocal both begin with R. Okay, so that one's easy. The equilibrium constant is also proportional to the coefficients, and we know that since it's proportional coefficients, that changing or doubling our reaction by comparison, so here's 1 and 2 going to 2 and 4, changing our coefficients will affect our Kc, and we look here, sure enough, increasing that scale, we would end up squaring our equilibrium constant. So doubling coefficients would lead to you squaring Kc. So Kc squared. Okay. If it was tripling, then it would be Kc cubed, quadrupling Kc to the 4th power, etc., etc. Okay. So, the following equilibrium concentrations were observed for the Haber process at 127 degrees Celsius. We're given our concentrations, and we're told to calculate K for the different situations. So let's do it. We need our equilibrium expression. Here is the Haber process. It's in the forward direction. We've got our NH3 squared. I'm sorry, I should have done brackets for that. Brackets NH3 squared over N2 and my H2 cubed. I'm going to plug in my numbers. 3.1 times 10 to the negative second. This is molar. I'm going to leave it as molarity. And this is squared over 8.5 times 10 to the negative first molar, and 3.1 times 10 to the negative third, and then I'm cubing that. Okay, make sure my brackets are clear here. Cool. So I'm going to go through, do that in my calculator, get my K value. So this is the only one I have to do a ton of real calculation for. Okay, so 3.1. All right, 3.1 e to the negative second squared. That part's easy. Divided by my reactants, I said 8.1, was it 8.5. 8.5 e to the negative first, and this is times 3.1 e to the negative third, and this one we are cubing. Let me double check, make sure I read that right. Yep. And I get a value to 2 sig figs of 3.8 times 10 to the negative fourth. Yeah, it's 37950, and that leads me to 3.8 times 10 to the positive fourth, not negative fourth. I'm sorry. 3.8 times 10 to the fourth. So my K, this is my K here. All right. So now they want to know, what is my K in the reverse direction? Well, what word did I say to keep in mind when you hear reverse? Reciprocal. So I need the reciprocal K, right? So 1 over 3.8 times 10 to the fourth. So 1 divided by 3.8 e to the fourth. All right, and I get 2.6 times 10 to the negative fifth. All right, 2.6 times 10 to the negative fifth. All right, so this is for the reverse reaction, and this is for the forward reaction. Let's evaluate these two Ks real quick. Which side of the reaction is favored? Should have said the product side. Why is the product side favored? Has a larger K, right? There's more products, it's got a larger K. You can confirm that the reverse reaction is not favored because it has a small K. So you can look at that one of two ways. All right, and then the last one, this one, it wants us to calculate the value given by the equation 1/2 N2 3/2 H2 and NH3. Well, if we compare that to the original, we said the original is N2 plus 3 H2, and then we get 2 NH3. So we have our original value. Our original value was what, 3.8 times 10 to the fourth? All right, 3.8 times 10 to the fourth. Well, if we're having our reaction in this case, then everything would be to the 1/2. So in other words, we're taking a square root. So square root of 3.8 e to the fourth, and we get 194.9. If we're doing that to 2 sig figs, it's 1.9. So this would be 1.9 times 10 to the second. So this is also 190. It's the same thing. Okay, pretty straightforward. Now we also have the reaction quotient. What happens when we have concentrations that aren't the equilibrium concentrations? Well, the reaction quotient is the exact same thing as the equilibrium expression. However, the concentrations we're given, we can express for these circumstances that are not at equilibrium. So it's the same ratio, but not necessarily at equilibrium. There is a time where K and Q are equal. When K and Q are equal, they are at equilibrium. So that part's nice. Now, if we're comparing K and Q, if Q is less than K, we're going to proceed in the forward direction. If we think about it, that means here, products are typically larger. And the denominator is normally small. But here we're saying that it's small and large. So we want to shift in that direction, okay? Now the other circumstance is when K is greater, or sorry, when K is less than Q, that means that this is, it's reversed. This is large and this is small, but then the K is got a small numerator and a large denominator. So we want to shift to this side, which means we're shifting back to form reactants. So keep that in mind as we're looking at the comparison between Q and K. So for the synthesis of ammonia at 500 degrees, the equilibrium constant is 6.0 times 10 to the negative second. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. Okay, so synthesis of ammonia. Ammonia is NH3. This is still the Haber process. So we're going to still use N2 plus 3H2 and our 2NH3, okay? But we're given our normal concentrations. So my Q quotient is the same thing. I still have my 2NH3. So I've got NH3 squared. I've got N2, and I've got H2 cubed. All right, so let's plug in and compare. Okay, so we've got 1.0 times 10 to the negative third squared. We've got 1.0 times 10 to the negative fifth, and we got 2.0 times 10 to the negative third cubed. Let's plug that in, see what we get for Q. All right, so 1e negative 2, sorry, negative 3. 1e to the negative 3, that is squared, divided by 1e to the negative fifth times 1e to the negative third. This one's cubed. All right, let's double check. Yes. Sorry, it's supposed to be 2.0 to the negative third. Apologies. Two e negative third. Okay. All right. So we get a very, very large Q. Okay. So 1, 2, 3, 4, 5, 6, 7, 1.3. Oh my gosh. 1.3 times 10 to the negative 7th, I believe. Or positive 7th. 1.3 times 10 to the 7th. Let's go back. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. All right. And that is definitely way greater than my K. So which direction is it going to shift? It's going to shift to the left. Shift left. Okay. Go ahead and calculate these last two on your own. And tell me which direction it shifts. Okay. Okay. Here we should have gotten no shift. They should have been equal to each other. Try C. Okay. Here we should have gotten that Q is less than K, and therefore it will shift to the right. Okay. That is all for today. Have a great day.